Welcome to everyone who's listening and watching. Appreciate it. I thought what we would do today is, first of all, kind of go through a brief introduction of the products, just so you have a feel for them. And then after that, because we have such a mixed audience, I'm sure, and your understanding of expansion joints and the concepts, after the product overview, we'll kind of get into what I consider to be the critical pitfalls that you may have to watch out for when using expansion joints, namely thrust load and the implications of that. And there's a lot of different stuff around that can screw you up with these products. So I want to make sure we cover that. And then one or two other pitfalls and important concepts that surround these products and confuse people. And in fact, many pipers like to avoid them altogether because of these kind of tricky pitfalls. But once you understand them, it's no big deal. But if nobody's laid it out for you, then you might not understand these very important concepts. But anyway, to get us, and if, by the way, and I hope, have time after this, if anybody has any specific comments, because of course this is kind of designed for a middle of the road, in someone who's informed middle of the road on expansion joints. So if you have a more basic question or a more advanced question at the end of this, that would be great. And I'm ready to handle that. But we'll go over what I think is the most important items. So quickly taking a look at the products, the types of expansion joints, really. We break them into families. We have the metal expansion joints first and foremost. And I'm going to click on this family. We can take a look at the choices here. And you see there's any number of models of metal expansion joints. There's the basic, sometimes referred to as bellows type, or metal bellows. That's another term that people use for metal expansion joints, although even these down below, these other products look like they don't have a bellows, but they do. They're buried inside of the housing. So referring to them as bellows is acceptable shorthand. But if you look at just one of the basic joints, our Model NLC, for example, you'll see different things. Normally, they're provided with a flanged end or a weld end, mostly flanged, any different type of flange, of course, that you want. And those can be removed, of course, so they're more popular than the weld ends. Notice a couple things about the data, and we'll get back to this later. There's such a thing as the spring rate, because when these get compressed or moved, they act like a spring. And so it springs back and tries to push down the pipeline into the anchors. And so it affects your pipe supports. And then the even more important effective area. The effective area is part of this concept of thrust load, which we'll get back to later. Now, some of you who use piping programs will note that when you put in an expansion joint, it'll ask you for this data. You might not completely understand why and what it's doing, but it'll ask you for this, and it's unique to expansion joints. Pressure, and so on, temperature, all those things are any piping component, but these in particular, you need to know the movements available, and you need to know the spring rate in the effective area. So this is a typical bellows expansion joint. I'll mention just a couple others just because there are special cases that are really important. The EP expansion joint, this is called an externally pressurized. And we have a training video, which we're going to see some things. If you look in the training video, it's 15 minutes long. It'll show you an illustration of this that's moving so you can understand how it works. But the bottom line is that you get a lot more axial movement out of this. Now you get when you're talking about expansion joints, of course, you're talking about controlling movement. There's an axial movement. That's the most popular, the most common. That can be either compression or extension. Compression, very, very common because as the piping heats up, the thermal expansion compresses the joint, and you need to have a metal bellows that will compress in the axial direction. This joint does that extremely well, up to 8 inches of compression. So you go back to that other bellows, and this one and these other ones are more likely to give you a couple inches. Sometimes they can go 3 inches and so on, but it's important to know about the externally pressurized in case you need to consolidate. You won't need as many joints. It's a simple thermal expansion application. There's also the compensators. These are up to 4 inch and they're used commercially for heating and plumbing systems. Again, a lot of movement and something you should know about. But that's it for the metal joints as far as we can cover on this brief introduction. Now, if we go back and we go to the next family, the next important family, the first two are the most important two, perhaps, rubber expansion joints. Well, rubber expansion joints don't take as much heat. They can't take heat like the metal. Generally speaking, you're talking about 200 degrees or so. They're available in different elastomers. Some elastomers can take a little bit more heat. And then, of course, chemical compatibility. Rubber joints, though, in general, in addition to being low temperature, you can't really expect them to last, the life of a plant like you maybe can with a metal bellows. They're not going to last as long, but they do a very good job of absorbing vibration and moving laterally. So very important. If it's low temperature, you might want to strongly consider these. Now, if you look at the first one, the ultra spool, this is called a spool type. And if you're specifying a joint, this is probably what you want. It's a workhorse. That design has been around for a long time, and it's very robust, gives you a good seal, full rubber face, and makes a nice seal. So this is the first thing to think of when you're thinking of a rubber expansion joint. There's double convolution, double arch, triple arch in different types. There's a Teflon lined version. But the other thing I wanted to point out was the secondary type. This isn't the spool type. This is a sphere type. Those are the two terms you're going to want to know for rubber expansion joints. The spool is great. This type is cheaper. It can still take a good amount of pressure, though. It uses flanges that are not backing rings with a rubber flange, but a metal flange. Usually the holes are tapped, so you don't need backing nuts. It has a rubber lip for a sealing surface, which makes it not as good of a sealing surface as the spool. But they're popular as pump connectors. This is where they get used a lot because they absorb vibration well. They're good in high pressure, and they can handle the vibration, and they're not that expensive. So it's a popular option for a pump connector. Those are the two types you have to know about: the spool and the sphere. So those are rubber expansion joints. So that's metal, that's rubber, and we got Teflon. Teflon has these three simple ones. I would not exactly call these robust, but they're cheap. And you got three different ones because you get more movement as you go from the fewer convolutes to the more. Again, Teflon lined rubber, we got Teflon lined metal. So if you want to go up to more robust still and higher pressures, these two are options. In addition to Teflon, it's worth noting that we also have PVC and CPVC joints for plumbing systems and the like. doesn't have to be, but those are an important option if needed. So that's what we have for the PTFE and PVC. One more is the flexible loops. Now this one we're going to get into a little bit more later because it's a issue with the thrust load, and this is important to understand as an option once we get into this thrust load thing. So we'll come back to this one, but you can see what they look like. Normally they got two legs, a braided metal hose separated by a return elbow. They can be oriented downward like this, or upward, or even out to the side. In fact, out to the side is one of the more popular ways to orient it. In this case, they don't come in pressure classes like the others normally, but they go up to 12 inches. 12 inches, you can get a 220 PSI. What do you do if it's bigger than 12 inches or you need more than 220 PSI? Well, you go to this thing down here, the special design we call a universal U-loop. Instead of braided metal hose, we use what's called a universal bellows type expansion joint. And now you can make them as big as you want and as high pressure as you want. So those are the loops. One last one worth mentioning is the braided flexible connectors. Notice they're not called expansion joints, flexible connectors. The braid here, whether it's on any of these different models, the braid prevents it from expanding. It works like the Chinese finger puzzle that you may have seen, where you try and pull it apart and you can't because the braiding gets more and more taut. And if you do try and compress it, it will compress, but you don't want it to, because then the braiding gets loose, called bagging, and now the pressure rating of the piece plummets. This is only good for vibration, really, on pumps mainly. So you can use this version as a flexible pump connector for vibration movement, or you can use a rubber one. Those are the most popular. But it's an important part of our flexible piping solutions, these braided connectors, so I mention it. But as far as expansion joints are concerned, the metal and the rubber are the conventional ones that have been around for a long time and are well understood. And the flexible expansion loops are important because of they handle the thrust load in a way we'll get into, and have really grown in popularity in the last 25 years. Now they're mainstream. So that's pretty much an overview. And what I'd like to go into next is this central issue of thrust load. Because whenever there's some problem with an expansion joint in the field, 99 out of 100 times it's related to this. So this is what the designers screw up with because they don't understand it that well. And the other thing is the use of pipe guides, which we'll mention briefly later. Well, we do have an education video, couple. We have one specific for metal, specific for rubber, and then just kind of an overview. And it's 15 minutes long. I recommend that anybody who's serious about it take a look at this as well. And if you were to start it, you get it rolling. Now, the reason I mention it, in addition to the fact that I think it's important to know about and to learn more if you want, is because I'm going to get into some things that are in here. I'm going to use some of the things from the video in explaining this thrust load issue. All right, so the first thing is, what is thrust load? But before we get there, I want to show you one thing about options for a metal joint, because one of the options is going to be important in our discussion of thrust load. But let's take a look at the main three options for the metal expansion joint. So first you got the liner. Now a liner can slip in like this. This is called a top hat liner. Looks like a top hat, slips in. And now you can easily take it out if it ever were to wear out and put in a new one. You don't have to do it this way. You can do it with, so it's fixed on both ends and has a telescoping effect. Why would you want a liner? Extremely high flow rates, number one, and abrasive material. So that's the liner. But so it's important to know about that, but that's not the main thing. Then we have a cover. The cover doesn't do anything but protect the bellows from miscellaneous damage. So if you feel like that may happen, where it might be susceptible, there's traffic, or somebody might drop something on it, because once you hit the bellows with a hammer, it needs to be replaced. So you may want the cover. But here's the option that I want to get into, because later it's going to affect our discussion on thrust load. Tie rods. Okay, so tie rods start by us at the factory welding on these lugs. Then you bring in the rods. The rods slip through the lugs, and then you get you fix it on either end so it can't expand normally. There is the option to leave a gap if you want to be able to move axially in extension. However, as we'll see, usually when you put on tie rods, the functionality is to simply prevent it from expanding. And some people think that will help with thrust load, but I'll show you why that's a little less than you might think. I was confused by this 20 years ago, and so I like to make sure everyone understands this. All right, so that's that part. Now, what is thrust load, though? It's a confusing concept for those that haven't been initiated to it. Many people don't understand it even after they hear it 2 or 3 times. So don't feel bad if you don't understand it, but I would expect most of you guys out there will. So the way we show this in the video, what a thrust load is we start out with an example of a straw, one of these bendable straws that's got this bendable portion in it. And let's say we were to blow on the end of it and cap. This end is capped, and we're going to blow on the other end, and let's see what could happen. First of all, you see how this piece stretches out if you pull it. Now you blow, and what happens? You get a force on the end here that stretches out the so-called bellows type joint here. You can see why this would happen. In the straight portion, it's also under stress from this force, but it's stiff enough. It's designed, in the case of a pipe, to withstand that load. It's not moving, it's not going anywhere. However, this portion is not designed to handle that load in the axial direction. And so it extends. It'll extend all the way out. So this is what the thrust load concept boils down to. The system is pressurized. And just because there's no cap on the end, you still get the same effect of a cap because you got the twists and turns of the piping system. Eventually, it acts like a cap. So there's a force trying to pull apart our bellows if we put one in the line. So that's what thrust load is. And it is much larger than people guess because it depends on the cross-sectional area of the bellows, called the effective area. You multiply that by the pressure. Well, that can get very large very quickly. So that's what we have to consider when we're talking about thrust load. Somebody calls up, they say, hey, we had a failure and the bellows seemed to stretch right out. We know immediately it was from the thrust load and it wasn't handled properly. So that's what we're talking about with thrust load. Now, if we move on, let's take a look at, if I can get behind this, hang on. Okay. Now, here we have a representation of a piping system. Pipe, it's got two anchors on either end. And of course, these anchors wouldn't be this close. They'd be way, way down, maybe 100 feet away or whatever. And you've got a straight run of pipe, two anchors, one bellows. And here we're going to watch what happens with pressure and the temperature as they change. Because, well, let's take a look. Let's see what happens here. So if I start this animation, we see the pressure rising. Now, as the pressure is rising, the stress on the tie rods that we have in here is continuing to grow because it's preventing the joint from expanding. So the joint is trying to expand, the tie rods prevent it from expanding, and they're under stress. So you might think, hey, problem solved, just put in tie rods. Well, let's continue on. So the pressure is all the way up. Now we start the system rolling and the temperature goes up. What happens is the temperature goes up, the pipe is expanding away from the anchors on either side, compressing the joint. When the joint compresses, the tie rods now become disengaged. They no longer they're no longer handling that stress. They're no longer handling the thrust load. As soon as they are no longer engaged, now that stress transfers to the anchors. And the anchors are getting stressed, you see, as the temperature goes up. Tie rods are doing nothing anymore. They're sitting in there loose. But sometimes engineers make the mistake and they think, oh, I'm going to put tie rods in and that'll handle my thrust load problem. Not quite. So the temperature keeps going up. Oh, so much that these anchors were not designed for that high thrust load and can fail. That's another thing that happens. We see people calling us up and saying, well, the anchor failed. Of course, the anchor fails, then everything else starts to go to heck. But anyway, this is what can happen. And so tie rods might not be doing the job of handling the thrust load you thought. So let's keep going here. Now, if I may, there was, if I can get this down, and we'll go to the next one. All right, there is a special exception to the tie rod rule. And it's such an important exception that I bring it up. There's other ways to handle this, but this is a very key one that you should be familiar with. As we start out looking at this, we see this is a lateral movement. Metal bellows do not move very far laterally. They're best in compression. But when you try and move them laterally, they're stiff. And so they don't move very far. Well, there is a solution to that. And that is called the universal type expansion joint, where you use two bellows with a piece of pipe in between. You got the piece of pipe in between. Now, each bellows rotates and gives you an effective lateral movement that is significant. If you lengthen the center spool, the longer it gets, this is an extreme, the more lateral movement you get. So this kind of demonstrates that. But okay, that's great, Paul, but what does that have to do with tie rods? If you put tie rods on a universal configuration like this, tie rods, they may stretch all the way across, or they can go across each bellows separately. Now the tie rods stay engaged. You get all this lateral movement with no thrust load because the tie rods do not get loose for lateral movement, only axial. So if you put in tie rods, That configuration is called a tied universal. Popular because if you do certain things with it, you can kind of move the, use a Z bend type configuration, use this in the Z. You get a lot of movement and no thrust load. So that's why this is an important thing that I thought needed to be mentioned. Now, if we keep going, we'll look at what about rubber joints? Well, rubber joints, you can't weld on those lugs for the tie rods. So you have to do something different. To get tie rods, you have to use what's called control units for rubber joints. This is a control unit. This is one. It's got the rod and it's got two lugs, and you'll see how this works in a second as we go. So in the case of the rubber expansion joints, you're going to have to put this on in the field. The contractor is going to have to put it on in the field. See here from the illustration, you got a breach in the pipe. The joint comes in. This is a spool type. You got these backing rings that come on, and you start to bolt it up. And then you want to put on the control units with the so-called tie rods. But this is how it goes. You get partial installation, then you put on the tie rods, the control units. These lugs, these gusset plates, as we call them, go on like that, and then you can put the rods in. And so it does the same thing as tie rods on the metal joints, but doesn't use welded on factory installed lugs. It uses these pieces to allow for field installation. So that is how you do it for rubber. And by the way, with rubber, oftentimes what you're doing is not thermal expansion or just a little thermal expansion, but instead are doing a lateral movement because you're getting settling. So if you get some kind of settling of the piping systems, the piping supports, the equipment it's attached to, or anything like that, that's going to result in a horizontal line or even in a lateral movement. So the tie rods, the control units that are placed on these rubber joints will handle the thrust load because they are not being compressed. So very often you'll have those tie rods specified with the rubber joint so that the thrust load is not an issue for the supports, the anchors. Because, why? Because you're not getting thermal compression, you're only getting lateral movement. If you do expect it to move because of thermal growth, those tie rods, just like the other ones, are going to disengage, and you're not going to have the absorption of the thrust load through the rods, but rather it'll be transferred to the anchors again. So you have to keep that in close mind. So that's a lot with the thrust load. Now there's another interesting twist to this, and that is these loops that we were talking about. They were designed because they do not impart a thrust load at all. How is that possible? Well, it's possible because the two legs are perpendicular to the pipe. When the pipe compresses, these move laterally. So the braid stays engaged, taking the thrust load, even though there's an axial compression. So that's the main idea behind these products. No thrust load, and they move well in all directions. Axial, lateral, angular, you name it, they can move very well, and they're not that stiff either. So the fact that they don't impart a thrust load on the anchors, you're not messing around with tie rods trying to make that work and it doesn't work and so on. That's why these have grown so much in popularity. That's one reason. The other reason is that they move so well in all three directions. So if this is an exaggerated movement, but it kind of gives you an idea, and then we'll see someone moving it by hand. Here's one you can tell, because sometimes it's not intuitive how this works, but you can see here how easily it moves in all directions. So including random movements like this right here. So here's a random movement. Why is that important? Because they're also used for a different type of movement. In addition to thermal expansion, which is key, seismic movements. So if you need seismic protection, movements in all three directions, and the random, this is perfect for that. So it's important to understand how they work. But here's an example that we use that shows you in real numbers how this thrust load plays out here. Well, first of all, we take an example, piping example. This is a 6-inch line, 150 PSI. Here's your anchors on either side. You can't see the other one. Here's the expansion joint in the middle, a traditional expansion joint. When it's under this pressure, it's transmitting the thrust load down to the anchor, most of which is this 12,800 pounds. So again, you get something bigger than 6-inch, you get up to 20-inch, 150 psi. It goes up like crazy, and now this load is going to be tremendously higher. But even here with the 6-inch example, it's almost 13,000 pounds. So this is your traditional metal expansion joint. Now, there's another traditional option. Handle the same thing. Oops, here we go. All right. And that is a hard pipe loop. You can get that same movement with a hard pipe loop. Oh, okay, let me go back a little bit. All right. So you got this hard pipe loop, but of course it's so large. 13 feet, 6 foot 6 inches. And you still get some of this going on. Go back here. All right. So some of the loads being transmitted from the stiffness of this hard pipe loop. Now, I keep messing that up. Sorry about that. Here you've got a flexible loop. And you see, of course, it takes up a fraction of the area that you're getting there. But the other thing to notice is the loads on the anchor plummeted. So here's your three options, and you can see where there's a place for the loop, the flexible loop in that family of options, because the thrust load is non-existent. And so now all you're dealing with is a very low spring load when this compresses. And so the load on the anchor is down to nothing, a fraction of what it was with this type of metal expansion joint. So there's your loop, and there's why thrust load comes into play. Every one you pick, you've got to deal with this thrust load one way or another. It's not like you can just cut a hole in an existing pipe and then think you got no new loads when you put in an expansion joint. You do. So that's what we have there. Now, there's the spring load that I mentioned as well. The spring load, again, is something that's unique to expansion joints. And it doesn't usually add up to anything near the thrust load, but it's another consideration. You have to know how much it's going to move, and you multiply that by the spring rate to come up with the load on the anchor. Of course, if you're using a piping program, it asks you for the spring rate. The movements are calculated automatically, and so it'll figure the spring load on all of your supports, as well as the thrust load when it asks you for the effective area of the joint. But knowing the concept, knowing what's behind it, even if you're using the program, is highly beneficial to getting your loads down and getting your ideal piping system. So that's that. And that's pretty much the bulk of it, but I wanted to mention another important one, and that is the use of pipe guides. In the case of expansion joints, metal expansion joints especially, here we have our system again. When it's under pressure, there's a load, thrust load on the anchors. The anchors push back. And when the anchors are pushing back and you have a joint in a line like this, it's susceptible to buckling. So it's not like it's going to be perfectly compressed on its own. This force either way is going to likely create a buckling effect. So when you're using metal expansion joints, especially, you need to use guides. And they need to be placed at regular intervals that are defined here in this table. This is not the Flexicraft idea. This is the industry. The industry dictates where these go. And again, it's based on buckling theory and how often you need them. What are the guides? Well, the guides allow for axial movement, but prevent lateral. So you're not going to get this buckling effect because it won't allow movement in the lateral direction. It'll keep the movement nice and straight on the for a thermal expansion compression. So if we look at there's two main types of guides: spider and slide, and they're two different concepts altogether. Spider guide, very popular. And the way it works, the red represents the pipe. And then this X spider is clamped to the pipe and moves with the pipe. So the spider moves inside this housing to slide back and forth. But it doesn't allow lateral movement, so it keeps it stable. But here's the thing about these. They're not technically a support. They're a guide. A support can handle a certain amount of load, a certain weight, or other loads. This isn't really rated for much load, so it's referred to as a guide only. Popular, but you're going to need to use other supports in your system. It might be a simple hanger or something, but it's something that allows some movement and doesn't rely on this, though, to handle the weight or any other loads. However, the other type of guide, slide guide, small diameters, mid diameters, and bigger diameters. This one is trapped from moving anywhere except axial by this piece here. You weld your pipe up on top. If you don't want to weld, you can use clamps. If you don't want to weld down to the base there, you can use a bolt down base option. But the big difference is these are supports. These can handle a load. And in our submittal sheet, it shows you what the load is. So now you can use this as your support all the way up and down if you like. It'll handle the weight of the pipe and the other loads where the other one would not. Again, I mention this because this is what can screw you up. Not using the guides, not having them placed properly will give you a problem. So if it's not a thrust load issue that created a failure, it's improper guiding that created the failure. And they're kind of related because the guiding is needed because of the thrust load in the first place. So anyway, so there you go, guides. So you got to handle the thrust load right, you got to handle the guides right, and when you do that, you're going to have a good outcome, positive outcome every time with an expansion joint if you got the pressure and the temperature and the movements right. But the guides and the thrust load issue must be dealt with. So those are the important points that I thought we should cover today that are going to be universal for any piper, regardless of your experience level. But of course, there's any number of things to go over besides this if we had more time. I do recommend the video, kind of fill this out a little bit, but and it's only 15 minutes, but that's what you have to worry about in our book. So anyway, there's as much time as we have to go over these expansion joints. And I guess our next step would be any questions or anything that anybody wanted to bring up.
Okay. I'm just checking to see if there's anything in the chat. There doesn't seem to be anything in the chat.
Okay.
One thing that I thought about when you were talking about the guides, traditionally, well, we're talking about pipe shoes as well, but the guides have to be the same height. Traditionally, they've been in like a standard height of about 4 inches. My understanding for that reason, because I've seen some projects that were done and they were using 5-inch high guides and all kinds of weird heights. And I couldn't figure out why. Do you know the history behind the 4-inch high pipe guides and pipe shoes? Is it just because that will accommodate the most common insulation thicknesses that you'd see in a refinery?
Right. That's a good question. One of the main things about spider guides is, of course, they're often used in insulated systems. So for an insulation, what normally contractors do is they take this housing, and you see the gaps here. There's gaps in between. And if you make the housing bigger, the gap gets bigger. And so usually what happens is we ask the contractor or whoever, how much insulation are you using on the pipe? If they say 2 inches, we know this has to be a certain thickness in order to accommodate that, where they can stuff in loose insulation. So that plays out down below here. Here's your pipe size. How much insulation do you have? What's the gap you want? Well, I got 2 inches of insulation, let's say, and it's a 4-inch pipe. 2 inches of insulation, 4-inch pipe. That means a model 27 guide. And over here, model 27 tells you all the dimensions. And so now you have enough room to put in 2 inches of insulation. If you want to go the expensive route, you can buy it pre-insulated. You tell us how much insulation you want. We insulate it ourselves. It's a special design. But that's what you're looking at there as far as spacing and to your question. Now, the other question is, what about the length of the feet? That can be adjusted to whatever you want, but normally people will put it on some kind of pedestal and change the height of the pedestal in order to get the proper center line for the pipe. Did that answer your question? I'm not sure.
In a way, because I'm thinking of in a pipe rack situation where you're going to have multiple shoes and guides. In the dimension A, which is from the center of the pipe to the underside of the support leg there, like really what you would have is you would have a dimension to the bottom of the pipe, which is generally, like I said, it's almost always 4 inches, unless you have thicker insulation.
Mm-hmm.
So I was just wondering, because that dimension seems like it could vary. Like
it can vary, and there's 2 ways to handle that variation. One is you can buy the guides from us with that A dimension being what you want. Okay. But if you want to use the standard, which is shown in the table, that A dimension that you mentioned, it's just you vary what it's mounted on, not part of the guide. You mount, I've got some representations of different kind of pedestals that these might be on.
Okay.
And it's so you adjust the height of what you're bolting or welding the guide to, and that's how you change that dimension. But if you're going to use the standard A. Now, there are special designs for vertical runs that are going through floors, and we have, they wouldn't be oriented this way. They come without feet, and then they're special, and you can use them in that way. Again, beyond the scope of our discussion today, but it's available. Also, note here, if you need very long travels, like you're using one of those expansion joints that gets the long axial movement, the externally pressurized. Notice how the spider is so much longer because you don't want this to move 8 inches and then have the spider fall out of the housing. So that's why we recommend normally anybody who is specifying or buying a metal joint, you might want us to help you pick the right guide in all the details as far as the movements and so on.
Okay, are there any further questions?
Have a
Harsh
look in the
Sharma.
in the chat, Paul, if you had a look.
Yeah, I just
It's
saw that.
Yeah.
Other than standard ASME B16.5 flanged ends for joints in lines connecting to rotating equipment like pumps, do you offer joints with custom end connections to match pump vendor flanges?
Oh, yes. Of course, we can do anything you want. I mean, that's for certain. But we normally find pumps do, go with ANSI flanges, whether they're 150 or 300 pound or 600 pound or whatever. But they normally are. But if they aren't, no problem. All you got to do is give us the flange hole information, the bolt circle diameter, the size of the holes, and the number of holes, and we go ahead. Now, what you normally see this as an issue on is not pumps so much as low pressure air systems or gas systems. Now, I didn't mention any of those types, but that's a whole duct expansion joints is a whole other topic. And those can not only come special with round flanges that are going to be unique because of the fan or blower manufacturer, but they might even be rectangular. So of course they're going to be custom made. But as far as the standard joints, yeah, we can make rubber joints, metal joints, any flange that you need, we can make them match.
Okay. Well, there doesn't seem to be any other questions. Oh,
Okay.
I see Bill has a question. Are there limitations to flow rates? I'm wondering about flow-induced vibrations and other issues
Yes.
where there might be flow-induced vibration in, say, hose U-joints. Is there a need for bracing?
Normally, as I showed before, sometimes there is a high flow rate, and it can cause a flow-induced vibration. We run that as part of our calculation, and we double check. If it's high enough, the solution is normally a liner, like I showed earlier, because that's when you use a liner more often than abrasive material, which is the other reason to use a liner. But the liner usually is the solution for the flow-induced vibration under the high flow conditions, which we do have a check for. And so, if you suspect that may be the case, the safe bet is to just get a liner because it doesn't cost that much more. There's no harm in getting it. And so that'll definitely take any doubt away.
Okay, I think that looks like it. There don't seem to be. Oh, from Shihata, what is the maximum lateral movement the rubber joint can accommodate? Specifically, it is if it is assigned in high settlement tanks.
That will be shown under each model. It varies by model and it varies by diameter. We take the standard ultra spool, and by the way, the ultra spool double is going to give you just about double that movement, and a triple. But the singles are going to be stocked, and these others are not. But let's just take a look at the ultra spool and pick a diameter, 6-inch, and then we go over to the lateral movement, 0.6 inches. So it's not a tremendous amount of movement, but as far as knowing what the movement is, you'll find it under the lateral column in all of the joints. Every joint is going to have different movement capabilities. Here's your lateral for a triple arch down at 6-inch being 1.9. So you have to check for each model what any of the movements are, usually broken down compression extension, together representing axial and lateral. There's a rotation, but again, that's rarely used. It's usually lateral or one of these other, but they always list the movements for each joint.
Okay, every time I say, well, there doesn't appear to be new questions in the chat, there's a new question.
Somebody puts in.
But I think maybe we are done.
Okay. Well, that's great. If anybody has any further questions later on that occur to you, of course, I'm available by email or a call. Happy to discuss any applications further. Of course, this is just an introduction, and there's different configurations and different design factors that we can throw in that we, of course, didn't have time to cover today. But we can pretty much do anything you want. Flexible Piping Solutions is our tagline, because we like to make sure that we're focused on the solution and not the product. But our breadth of product helps with our solutions, because we have pretty much every design that's available in the industry. And so we're not forced to pick one versus the other. We've seen many times where rubber joint manufacturer, every solution involves a rubber joint, as you might guess. But the breadth of our offering allows us to not have an inherent bias towards one type or another. But with all these various options, there's likely to be, an absolute best, especially when you consider the variations that we can come up with within each family here.
Paul, I see there's a message in the chat. Sorry. Do you supply the products in Canada, and do you have an office in Alberta or Ontario?
We don't have an office in Canada, but of course we do sell in Canada. So yes, we sell in Canada, but we don't have an office there. So, it is difficult for us to visit various locations in Canada, but certainly that's our second market. We have the United States primarily, but Canada's right there, number 2. And so yes, we do sell in Canada, but don't have an office.
Yeah, I think the issue there is probably CRN numbers.
Right. Mm-hmm.
That's the major consideration for
Right. And we do have CRNs for various ones, and can get others as needed. We certainly are well familiar with that, the CRNs and the process.
Great. Okay, if there are no further questions, I want to say thank you to Paul Berg for the presentation and answers to our questions. Hopefully I'll be able to get this up on our SPED YouTube site in a few days. So if anybody wants to watch it again, they can. Thank you everyone for attending. This was a well-attended session.
Definitely.
All right, thank you everyone. Thank you, Catherine,
Thank
for
you.
organizing it.
Pleasure.
Thank you, everyone,
Paul.
again. Thank you.
Thanks, Ed. Okay.
Thanks.
Bye-bye. Bye-bye.
Bye.